This video is from Unit 2 concerning bioenergetics and how energy is managed in the cell. We'll be looking at the first part about enzymes and then photosynthesis and cellular respiration. So before we do that, let's some of the basic concepts of energy. And so here you have a picture of a hydrolysis reaction. If you remember, hydrolysis is using water to break down um, using water to break a macromolecule, and when that happens, when bonds are broken, energy is released from those bonds. And you can see here on this graph the free energy. Free energy is the amount of energy available to do work. Well, as you break the bonds in the reactants, energy is released. So when the bonds are broken, that means that there is less energy at the end of the reaction than there was at the beginning of the reaction. This type of reaction is called an exergonic reaction. Hydrolysis reaction is called an exergonic reaction, meaning that energy is released into the environment. Sometimes these reactions are also called catabolic, like a catabolic reaction, because it's breaking something down. The opposite of this is an anabolic reaction, whereas there is more energy after the reaction occurs than before. This is like the formation of bonds, the storing up of energy into chemical bonds. Rather than being an exergonic reaction, this is called an endergonic reaction. And so this is basically the opposite of the catabolic reaction or the exergonic reaction. These two types of reactions are coupled regularly in living systems. And so here you see that we call this energy coupling. These two processes are united, and photosynthesis and cellular respiration are great examples of this. Whereas in photosynthesis, energy is taken from the sun, and that energy is transformed into some sort of organic molecule like a sugar. And whereas that in cellular respiration, that sugar is broken down and that energy that was put into it is taken back out. And then we use that energy to power cellular processes. And so this type of energy coupling is essential to living systems. Normally, any of these reactions that are taking place in our body, whether it be things that are reactions that are building molecules or reactions that are tearing down molecules, all of those reactions together are what we call metabolism. So metabolism is just the sum of all of those reactions. And so that brings us to this concept of kinetic energy versus potential energy. And these are words that you've had in your repertoire for some time, but it is important to make sure that we understand that kinetic energy is energy of motion. It's energy that is being used for something. It's energy that is currently being released. And so when the energy in chemical bonds is released, that represents kinetic energy versus the energy that's being stored in chemical bonds, which represents potential energy. And so here's a picture of a molecule that is temporary storage for energy, and this is ATP. We'll talk more about ATP in a moment. But ATP represents a molecule that the body uses to store energy very temporarily. It's not like sugar or fat or something like that that can store energy more long term, but this is the body's energy currency, essentially, is ATP. And then that brings us to a discussion on the laws of thermodynamics. In order to understand energy and how it works in living systems, we have to understand these two laws of thermodynamics. And the first law is this, that energy is not created or destroyed, meaning that you can't just make energy from nothing. You can't just make it. Also, you can't get rid of it. Energy never just goes away. It is simply transferred, meaning that it is switched over to another medium, or it's transformed. It's completely changed into another form. Like think of like a hydroelectric dam, where the dam uses the energy of the water to transform that energy into electricity. Well, you look at this picture of this cheetah eating this deer. The deer, it represents one form of energy, represents energy stored up in bonds. The cheetah will eat the deer and will get energy out in order to do the things that it does. The second law of thermodynamics states this, that every energy transfer increases the amount of entropy in the system, whatever system that is, ultimately in the universe, increases the amount of entropy in the universe. Entropy basically means disorder. It is unable to do work because it has a low state of order, whereas energy that's found in chemical bonds is all structured and ordered. Energy that's from the sun, electricity, these are relatively ordered forms of energy. Entropy is disorder. It is not a good form of energy. It is not a good form able to do work. Normally, when we talk about entropy and energy being lost to entropy, that energy is lost as heat. And so if you take this cheetah that's running, it ate the deer, now it has energy. It's not able to 100% efficiently use the energy from the deer, and you know that because when the cheetah stops and it's panting, it's hot, there's this heat that's being released, because when the body burns that energy, it's releasing some of that energy as heat because it's inefficient. And so this energy that's not good energy is related to entropy. That brings us to this equation. We have a way of measuring that and calculating that, and it's the Gibbs free energy equation. Gibbs free energy is represented by G, and free energy is the amount of energy that's available to do work. So again, we're not talking about heat energy, we're talking about good energy, like energy in chemical bonds or energy in sunlight. And so that energy, the amount of free energy available, equals the total amount of energy in a system, which is called enthalpy, you can see here. And then you subtract that, subtract the entropy times the temperature. Why is that? Well, if you think of enthalpy, or the amount of total energy in a system, there's a delta here in front of this. These triangles represent delta, and it's the change in energy, which is just the final subtracted from the initial, or the final minus the initial, and this is just the change. So if you have 100 to start with and you have 70 to end with, and there was a change of 30, you lost 30 energy. And so delta H, total amount of energy in the system, and then you subtract from that energy the amount of entropy, and it's going to be in some sort of energy measurement, probably joules. And why do you multiply that times the temperature? Well, as the temperature goes up, you would expect the amount of energy, or the amount of entropy, the amount of molecules moving around and bouncing off of things, to be higher. As the temperature goes down, that's going to decrease. And so what you have left over then is the amount of energy able to do work. And so again, this is a very simple calculation. So calculation is not going to be the limiting factor here, but it's simply an understanding of the concept. And so let's look here. The system there on, or this shows us a simple system that's closed. And in a closed system, what we mean by closed is no energy is coming in, no energy is going out. The system is 100% efficient. And so if a system is 100% efficient, there's no loss of energy to heat, and there's no need to put energy back in. And so this would be some sort of self-sustaining kind of energy. If you can invent that, by all means do so and solve most of the world's problems. However, this is not how most systems work. And so if you look at a system like this, if you look at a system like this hydroelectric dam, the energy from the water moving through this turbine is able to turn this light on. The energy from the light is available to do work. Well, how do we put this in terms of endergonic and exergonic? Well, let's think about it. If there's energy, a high amount of energy available at the beginning of the reaction, and then there's a loss of energy because the amount of entropy increased. And so what would you expect delta G to be? Well, delta G is going to be negative. And so there's this energy that's available because energy is released. This energy is available to do some sort of work. So this would be like cellular respiration, right? You start with glucose. That glucose is broken down, energy is released, and that energy is available. It's out in the open, it's out there to do some sort of work. Now, some of that's going to be lost as heat, is because there's a transfer, but then there's some of it that's available to do work. You take the opposite, the endergonic reaction. What's happening to the amount of entropy? Well, the amount of entropy is going to be low because it's being put into a chemical bond, it's being set into order. And so with the amount of energy, or the amount of entropy being low, delta G then is going to be positive, meaning that there's not energy available to do work because that energy is locked up in chemical bonds. In order to get that energy out, you have to break those bonds. You have to perform the opposite reaction. Photosynthesis is a great example of this. It's taking energy from the sun. So we'll, just to draw the sun here, that energy from the sun is being put into this product. Delta G is going to be high in that. If you take that same glucose, break it back down, you're going to see the opposite reaction. Delta G is going to be negative. And every time this happens, notice what's getting lost. Energy. There's going to be a loss of heat. And so this can only happen so many times before everything just kind of turns to heat. And so this shows you that idea here. Heat is getting lost every time. And so eventually, all the energy in the universe is going to be converted to heat. There are different kinds of ways that energy is used and performed, or work is performed in cells. And here are a few. One of those is mechanical work. Literally, cells and proteins and other structures moving around inside the cell, causing something to occur. Here's an example of a motor protein. These little motor proteins, they grab a vesicle and they carry it up the microtubules moving around. It's an example of mechanical work. It's literally things that are moving around. Transport work, this is the use of a concentration gradient in order to pass materials from a high concentration to a low concentration, thus creating energy to do work. And then you have chemical work as well. This is just the breaking of bonds to get energy out of those bonds in order to do some sort of work. And this last one is an example of what ATP does. ATP, it stands for adenosine triphosphate. The triphosphate is because of the 3 phosphate groups that you see here at the end of this molecule. And the magic of ATP is the energy that is located between the 2nd and 3rd phosphate bond. That energy is where the energy from ATP comes from. How is that? Well, if you'll notice, those phosphate groups are very negative, and negative things don't like each other. And so if you can imagine, if you've ever tried to push 2 magnets against one another from opposite ends, those magnets want to repel. If you could ever get them to stick against one another, there would be some energy there. You'd have to actually physically hold them in place to keep them from wanting to jump apart from each other. If you could harness that energy, then you could do something with it. And so ATP represents that kind of thing. The 3rd phosphate is kind of crammed onto there, and thus that energy is almost like a spring that decompresses and uses that for energy. And the cells use this to do lots of different things. Anytime that third phosphate is used to turn something on, turn something off, do some sort of process, that is called phosphorylation. That's just the energy from ATP being used in the form of that third phosphate to activate some sort of system in the body.